Hey guys, welcome back to part 2 of transforming polynomials, and let's just get started right away with the question. Okay, the question is, find a polynomial whose roots are 3 greater than those of x to the 4 minus 3x cubed minus 3x squared plus 4x minus 6. And now you realize that this is different from last part, as we're not dealing with multiplication or division anymore, we're dealing with addition or subtraction. So we can start off by defining this polynomial as a function f of x. We want to find a new function, g of x, which is equal to f of x minus 3. The reason why I'm defining g of x equals f of x minus 3 is that in the new polynomial that we're going to be finding, the roots are going to be r1 plus 3, and so on. And when we substitute r1 plus 3 into here, we just in turn get f of r, which is going to be equal to 0. And that is exactly what we want. And basically, we can just finish the problem right now. If we were to just sub in x minus 3 into the function, we would be getting So the problem with this is that you're going to have to expand all of these powers with binomial expansion, and you're eventually going to have to combine like terms, and then it's just going to take way too much time. So I'm going to be telling you an easier way or a much slicker way of solving these questions. Now what I'm going to be showing you in this video is how to find f of x minus 3 term by term. And to give you a visualized explanation of this is that, for example, if f of x minus 3 is expanded in a way such that it is like this, an xn plus an minus 1 xn minus 1, and so on to ao, we're going to be finding all the coefficients on x and the constant term. So we're going to be finding this, so on, everything in between, and ao. And since we can just slap on the x's at the end, since they're not going to be changing, they're all just going to be the same powers decreasing. We can just, all we have to do is focus on finding the coefficients on the x's. And the first thing we have to realize is that we want to find f of negative 3. And why do we want to find f of negative 3? Is that this f of negative 3 is basically what happens when we substitute x equals 0 into the function. And whenever we substitute x equals 0 into a function, we will get the constant term at the end. And if we want a visual explanation of this, let's say that we have the function this again to ao, and if we were to substitute x equals 0 here, all of these terms before it cancel out, leaving us with the constant term at the end. And this is what f of negative 3 is basically is. It's giving us the constant term at the end of f of x minus 3. Now I'm basically going to give you guys a disclaimer. To solve this question, you will need to know how to use the remainder theorem. And if you don't know what it is, you can basically just search it up online. It is not that hard. It'll probably take you about 10 minutes to learn. And what it states is basically that we have a function, g of x, or let's write in f of x divided by x plus x minus a. This is going to give us a new function, h of x, with a reminder of f of a as remainder. And what the remainder theorem also tells us is that we can write this statement above as f of x equals x minus a h of x plus f of a. And now if we substitute a equals negative 3, we basically have f of x equals x plus 3 h of x plus f of negative 3. And we can rewrite this back into the normal statement. You can write this as f of x as over x plus 3 is equal to h of x plus f of negative 3. Now we notice something very interesting here. We have here f of negative 3, and this is what we want to find from before. We want to find f of negative 3, as that is the constant term inside of f of x minus 3. But what do we do with h of x? We know that f of x is defined, and we can just divide f of x by x plus 3. But what is this h of x as? Well, to do this, we can manipulate this equation. Now we set x is x minus 3. Since x is just a variable, we can define it to be however we want. We can set this is going to be equal to f of x minus 3 over x equals h of x minus 3 plus f of negative 3. Notice that f of x minus 3 is the function that we want, and if we divide that by x, we're going to get another function of h. Subsequently, the remainder does not change, so we could work with whichever function that we want, and we would still get the same remainder every time. So what I'm basically saying here is that if we were to divide f of x by x plus 3, we would get the same remainder as if we were to divide f of x minus 3 by x. And the remainder is all that we're looking for. Now the reason why we're only looking for remainders here is that given this function, a more generic function, the remainder is we're looking for when f of x, let's say this is f of x, is divided by x. If we were to divide the whole thing by x, we were to just be left with this remainder. Now this is why we're only looking for the remainder, as we continue to divide by x on f of x, we would just keep on getting the coefficients and eventually getting all the coefficients. And thus we would know what the whole equation looks like because we have the coefficients and we can just replace all the x's back. And so if we work back with this function here, if we were to continuously divide f of x by x plus 3, we would get all of the remainders inside of f of x minus 3, which are the coefficients on the x's. And this is much easier as we know that f of x is defined, and we can just synthetic divide by x plus 3. And we can make this into a recursive solution, because since we know that h of x is going to be a function of f of x, so we can continuously sub h of x into f of x, and we get a new function here that we can continuously sub in, and make it so that this is a recursive solution. Now if we were to do synthetic division on f of x, notice that this is f of x, and we're dividing by x plus 3, so this is going to be negative 3 over here, and synthetic division is going to tell us that this is going to be negative 3, so this is going to be negative 6, 18, 15, negative 45, negative 41, 123, and 117. And what synthetic division gives us is that this here, 117, is going to be f of negative 3. That is going to be the remainder. And this thing here is going to be h of x. This is going to be the new function with these as the coefficients. So this is going to be x of 3, x squared, x, and that is going to be the constant term. Now we can make this into a recursive solution by saying that h of x is f of x as we go down into the x's, as we have already eliminated the constant term, so we want to divide this whole thing by x plus 3 again to get the new remainder. So we can define this as h of x divided by x plus 3 equals a new function v of x plus h of negative 3. And h of negative 3 is just going to be the new remainder, and h of negative 3 is also going to be the coefficient on the x in f of x minus 3. So again, we can synthetic divide this whole equation up here by x plus 3. Now synthetic division tells us this is going to be negative 3, negative 9, 27, 42, negative 126, and negative 167. Now we have the new remainder, and this is going to be the coefficient on x inside of f of x minus 3, and we're going to be given a new function, and it's going to be v of x, and we can continuously recursively solving this, and until we get to the 1 here, which is going to be the first term which is going to be the x to the fourth in f of x minus 3, by simply synthetic dividing by x plus 3. Now I'm not going to show you the whole thing, but all you need to do is keep on synthetic dividing by x plus 3 and keep note of the remainder, as that is going to be the coefficient of all the x's and the constant term inside of f of x minus 3. So in the end, you would arrive at an equation like this. X to the fourth minus 15x cubed plus 78x squared minus 167x plus 117. And this is going to be g of x. And we managed to solve this equation without having to use binomial expansion and expand the whole thing and eventually collect like terms and combine it back. We solved this equation by recursively dividing by x plus 3, and with the power of remainder theorem, we're able to know that the remainder is going to be the coefficient of the new function. So here we have a question. The roots of f of x are a, b, and c. And f of x is here, where f of x equals 3x cubed minus 14x squared plus x plus 62. And they want you to find the value of 1 over a plus 3 plus 1 over b plus 3 plus 1 over c plus 3. I encourage you to pause the video here and take some time to do this yourself. And we'll be right back. So I hope you had some time to spend on it, and I'm just going to be going straight to the solution. So notice here that we have a plus 3, b plus 3, and c plus 3. So the roots we're going to be finding is, first of all, they're going to be 3 greater than those of f of x. And we've just done that. And then we're going to have to flip this. And to flip this, we already explained this in part 1 of transforming polynomials. We're just going to flip all the numbers on the coefficients of x. And then we're going to find all of these added together, which we're just going to use Vienna's for that. So to find the new polynomial, g of x, which are going to have 3 times the roots of f of x, that is going to be f of x minus 3. And we already know that how to find this. We're just going to keep on synthetic dividing by x plus 3 of the original function f of x. So let's just get on with it. And so our new function g of x is just going to be 3x cubed minus 41x squared plus 166x minus 148. Now we have g of x. We want to find the new function, which are going to have roots of the reciprocal of g of x. And to do that, let's just define another function of h of x. And to find the reciprocal roots, all we're going to do is to flip the coefficients, as we learned from transforming polynomials part 1. And it's going to be 148, negative 148, x cubed plus 166 x squared minus 41x plus 3. Now that we have the function h of x with all the right roots that we have, we want to find the sum of it now. And we know that by Vieta's, the sum of the roots is negative b over a. And in this case, b is 166, and a is negative 148. And we want to find the negative of that, which just simplifies down to 83 over 74. And that is our answer. So I hope you learned something new about transforming polynomials that you didn't before, and thanks for watching.